spring 1940, and the Royal Air Force has a problem that's killing pilots faster than German bullets. Spitfire squadrons are limping back to their bases with stories that don't make sense on paper. The newest fighter in Britain's arsenal, the aircraft that's supposed to rule the skies, is being consistently outmaneuvered by Messerschmitt Bf-109s in one specific, terrifying scenario. Push the stick forward into a dive, and the Rolls-Royce Merlin engine coughs, sputters, and dies. For 5, maybe 10 seconds, you're a glider with a German on your tail. 10 seconds is an eternity when 20 millitulum cannon shells are closing the gap at a combined speed of 600 miles per hour. Fighter Command knows the statistics by late March. In 73 confirmed engagements over France and the Channel, Spitfire pilots report engine cuts during negative G maneuvers in 61 instances. That's an 83% failure rate on a combat move that often means the difference between getting shots on target or becoming a target yourself. Squadron leader Brian Lane of 19. Squadron files a report that lands on desks at the Air Ministry with coffee stain urgency. The 109 pilot pushes into a dive, we follow, our engine quits, he's gone. We're picking predictable evasion patterns because our aircraft won't follow our intentions. This is the crisis that pulls Beatrice Shilling into the story. She's not supposed to be at RAF Tangmere on March 23, 1940, but the Royal Aircraft Establishment at Farnborough has dispatched her to witness the problem firsthand. 29 years old, a motorcycle racer who holds speed records at Brooklands, she's one of only a handful of women engineers working on military aircraft. The establishment types at RA tolerate her because she's earned a first-class honours degree in mechanical sciences from the University of Manchester, and because her specialisation, engine performance under stress conditions, is suddenly the most critical field in British aviation. She watches from the dispersal hut as Flight Lieutenant James Leithart demonstrates the fault. His Spitfire Mark I climbs to 8,000 feet, rolls inverted, and pushes forward into a split S manoeuvre. The Merlin's smooth roar disintegrates into a strangled cough. Black smoke erupts from the exhaust stacks. Leithart levels out, and after 7 agonising seconds, the engine catches again. He lands and finds Shilling already on the tarmac, asking questions that reveal she's grasped something the pilots have been living with but couldn't articulate. "It's not the dive angle," she says, checking her notebook. "It's the acceleration vector. Anytime the aircraft experiences negative gravitational load, the fuel feed interrupts, which means you can't push, you can't pursue, you can't exploit an advantage if it requires forward stick pressure." The Luftwaffe, meanwhile, has no such limitation. Their Daimler-Benz DB601 engines use direct fuel injection, a system that pumps fuel into the cylinders regardless of aircraft attitude. Messerschmitt pilots can push, pull, roll through any axis without their engines missing a single combustion cycle. In the tactical chess game unfolding over southern England, the Germans are playing with a full set of moves while the RAF is fighting with half its options locked away. Shilling returns to Farnborough that evening with oil stains on her coveralls and a problem that's suddenly become personal. The Rolls-Royce Merlin engine is a masterpiece of 1930s engineering, but it's built around a technology that predates the Wright brothers. Carburetors work on a principle that's beautifully simple. Air rushing through a narrow throat creates low pressure, which sucks fuel from a reservoir into the airstream. The mixture atomizes, flows into the cylinders, and combustion happens. This system works flawlessly as long as gravity keeps fuel sitting at the bottom of the float chamber, ready to be drawn up through the jets. Every automobile engine in 1940 uses this principle. Every lawnmower, every generator, every piece of equipment that needs to mix fuel and air relies on gravity as the invisible hand keeping fuel where it belongs. Now flip that assumption upside down. When a Spitfire pilot pushes forward into negative G, everything loose in the cockpit floats upward. Maps, dust, the contents of the pilot's stomach. Inside the float chamber, fuel does exactly the same thing. It surges away from the jets toward the top of the chamber, leaving the pickup points sucking air. The carburetor keeps trying to pull fuel from a reservoir that's temporarily empty at the bottom. Air rushes through without fuel. The mixture goes fatally lean. Combustion temperatures spike, the engine detonates unevenly, and then it simply stops firing. The phenomenon lasts only as long as the negative G condition, but in combat, 3 seconds of dead engine translates to 400 feet of lost altitude and a firing solution handed to your enemy. Shilling runs the mathematics on April 2nd, 1940 in her lab at Farnborough. The Merlin's float chamber holds approximately 0.8 litres of fuel. At normal operational draw, that's enough for 12 seconds of running time, which means the float valve is constantly refilling the chamber as the carburetor feeds the engine. Under 1G conditions, normal flight, fuel sits at the chamber floor with roughly 1.2 pounds per square inch of hydrostatic pressure pushing it toward the jets. Push into negative G even momentarily, and that pressure inverts. The fuel experiences an upward force while the jets are still trying to pull downward. Physics doesn't negotiate. The fuel separates from the pickup, the engine starves, and the Spitfire becomes a liability instead of a weapon. The German solution, fuel injection, sidesteps the entire problem through brute force. The Daimler-Benz DB601 uses a mechanical pump that pressurizes fuel to 30 psi, then meters it directly into each cylinder through individual injectors. Gravity becomes irrelevant. The fuel line stays pressurized regardless of aircraft orientation. A Bf-109 can fly inverted for minutes, pull negative G until the pilot blacks out from blood pooling in their skull, and the engine never notices. It's technologically superior, mechanically complex, and expensive. Each DB601 requires precision machining of the injection pump, calibration of 9 separate injector nozzles, and maintenance procedures that demand trained specialists. The Luftwaffe has built their tactical doctrine around this advantage. Their pilots are trained to exploit it mercilessly, push into negative G the instant a Spitfire commits to pursuit, and watch the British engine fail like clockwork. Shilling's notes from early April show she's testing a theory about flow restriction. If the carburetor is delivering too much fuel too quickly during transitions, and if that excess fuel is what's sloshing around creating the starvation problem, then perhaps limiting the maximum flow rate would keep the float chamber more stable. It's counterintuitive, restricting fuel delivery to solve a fuel starvation problem, but the physics suggest it might work. The question is how to test it without rebuilding an entire carburetor system, and whether anyone at the Royal Aircraft Establishment will let a junior engineer with unorthodox ideas anywhere near a Merlin engine that costs more than a house. The Royal Aircraft Establishment's official response arrives on April 9, 1940, in the form of a 40-page technical proposal. Senior engineers at RA have convened multiple committees, consulted with Rolls-Royce design teams in Derby, and produced a solution that involves redesigning the entire carburetor assembly. The plan calls for a pressure-balanced float chamber with spring-loaded baffles, anti-slosh compartments, and a modified fuel delivery system that would maintain positive pressure regardless of aircraft attitude. Estimated development time, 8 to 11 months. Estimated cost per unit, £47 sterling. Estimated production disruption, complete halt of Spitfire deliveries for 6 to 8 weeks while Rolls-Royce retool their manufacturing lines. It's May 1940. France is collapsing. The British Expeditionary Force is about to be pushed into the sea at Dunkirk. Fighter Command has 331 operational Spitfires, and they're losing aircraft faster than Supermarine can build replacements. An 11-month development timeline isn't a solution. It's a death sentence written in bureaucratic precision. Squadron commanders are screaming for anything, any modification, any field fix that might let their pilots pursue German fighters without their engines quitting. The establishment response is to form another committee to review the implementation strategy for the pressure-balanced carburetor system that won't exist until 1941. Shilling reads the proposal in her workshop at Farnborough and makes a decision that will define her career. She's going to ignore it, not openly. She's too smart to directly challenge senior engineers who have 30 years of experience and connections throughout the Air Ministry. But she's going to pursue her own theory using her own methods. And if it works, she'll present results that make the official solution look like what it is: over-engineered institutional thinking that prioritizes elegance over urgency. Her approach is almost insultingly simple. If the problem is fuel sloshing in the float chamber during negative G, and if excess fuel volume contributes to that sloshing, then restrict the fuel flow entering the chamber in the first place. Not with springs and baffles and pressure-balanced compartments, but with a physical restriction. A washer with a precisely calculated hole drilled through its center. Install it in the fuel line feeding the carburetor. The restriction limits maximum flow rate, which keeps the float chamber from overfilling, which reduces the volume of fuel available to slosh around during negative G maneuvers. Less fuel sloshing means the jets stay submerged longer. The engine still cuts out, but for 2 seconds instead of 7. 2 seconds you can work with. 7 seconds gets you killed. The engineering establishment would consider this approach crude, inelegant, plumber's solution to an aerospace problem, which is precisely why Shilling doesn't ask permission. She requisitions a brass disc from the RA machine shop on May 4, 1940. The requisition form lists it as test material for fuel flow analysis. She takes it to her personal workshop, a shed behind her flat in Farnborough where she rebuilds motorcycle engines, and spends an evening with drill bits and calipers. The mathematics suggest a 0.06-inch diameter orifice for a Merlin third engine running at combat power settings. Too small and the engine starves at full throttle. Too large and it doesn't solve the negative G problem. She drills 6 test washers at different diameters: 0.55, 0.57, 0.60, 0.63, 0.65 and 0.68 inches. By May 7th, she has a collection of brass discs that look like oversized pennies with holes punched through their centers. Each one costs approximately threepence in materials. Each one can be installed in 15 minutes by any mechanic with a wrench. Each one might solve a problem that's costing Fighter Command its tactical edge in the battle that's about to determine whether Britain survives the summer. Now she just needs someone willing to let her bolt one onto a Merlin engine and see what happens when you push the stick forward. Geoffrey de Havilland Jr. is the test pilot who gives Shilling her chance. He's chief test pilot at the Airborne Forces Experimental Establishment, son of the legendary aircraft designer, and someone with enough institutional clout to authorize unauthorized modifications without immediately triggering inquiries from Air Ministry bureaucrats. On May 14, 1940, Shilling arrives at the Hatfield Aerodrome with her collection of brass washers wrapped in a leather tool roll. De Havilland has already heard rumours about the female engineer who tears apart motorcycle engines for sport and who's been asking uncomfortable questions about why the RAE's official carburetor solution won't be ready until spring 1941. The test aircraft is a Spitfire Mark Waffern, serial number K9795, pulled from a production batch destined for 54 Squadron. Shilling and a ground crew mechanic named Albert Foley installed the 0.060-inch washer in 22 minutes. It sits in the fuel line between the engine-driven pump and the carburetor inlet, a brass disc slightly thicker than a shilling coin, which is where the modification will eventually get its unofficial name. The washer doesn't require any modification to the carburetor itself, doesn't alter the float chamber, doesn't touch any of the complex metering systems that Rolls-Royce engineers have spent years perfecting. It just sits there in the fuel line, creating a permanent restriction that flow must pass through. De Havilland takes K9795 up at 11:30 a.m. The test protocol is straightforward: climb to 10,000 feet, roll inverted, push into negative G and hold it for as long as the engine keeps running. Standard procedure would expect the Merlin to cut out within 3 to 4 seconds. Shilling stands on the tarmac with a stopwatch and binoculars. The Spitfire climbs through broken cloud, levels out, rolls. From the ground she can hear the Merlin's note change as de Havilland pushes forward. The engine coughs once, a momentary hesitation, then continues running. 4 seconds. 5, 6. At 8 seconds, de Havilland rolls upright and the engine smooths out immediately. He makes 3 more passes, each time holding negative G for progressively longer periods. The longest run goes 11 seconds before he breaks off. Not because the engine quit, but because holding inverted negative G for that duration puts enormous strain on the airframe and pilot. He lands 28 minutes after takeoff and taxis to where Shilling and Foley are waiting. Before the propeller stops spinning, de Havilland is climbing out of the cockpit with a grin that tells the story. It still hesitates, he reports, but it doesn't cut. Held negative G through a complete split S, and the Merlin stayed alive the entire time. Rough, not happy about it, but it didn't quit. Shilling asked about performance at full throttle, whether the restriction starves the engine during normal combat power settings. De Havilland shakes his head. Maximum speed unchanged. Climb rate actually feels slightly better, probably because the mixture's running leaner and more efficiently. They test all 6 washer diameters over the next 3 days. The 0.55-inch version restricts fuel too severely. The engine loses power above 20,000 feet, where air is thin and mixture calibration becomes critical. The 0.68-inch washer doesn't solve the negative G problem adequately. The 0.60-inch diameter proves optimal, a Goldilocks solution that restricts fuel just enough to prevent float chamber flooding without starving the engine during normal operation. By May 17th, Shilling has her answer. A brass disc that costs threepence and can be installed by any mechanic in 15 minutes solves 80% of the carburetor problem that Ray's official committee expects to fix in 11 months with a £47 redesign. Now comes the test that matters: combat performance. On May 20th, Shilling brings her data to squadron leader Brian Lane at RAF Duxford. He's skeptical. 9 years of RAF service have taught him that engineering solutions promising easy fixes usually create new problems, but he's also desperate enough to try anything. Lane authorises installation of Shilling's washers on 6 Spitfires from 19 Squadron's operational aircraft. The trial will happen in combat, where negative G manoeuvres aren't controlled test protocols, but life or death decisions made at 300 miles per hour with tracer rounds stitching the air around your canopy. The problem with revolutionary ideas is that they threaten people who've built careers on conventional wisdom. When Shilling's modification reaches the Air Ministry in late May 1940, the institutional response ranges from scepticism to outright hostility. Senior engineers at the Royal Aircraft Establishment argue that restricting fuel flow is mechanically crude, that it fails to address the root cause of carburetor starvation, and that installing unauthorised modifications on operational fighters violates every protocol governing aircraft certification. One memo, dated May 28th, from an RAE department head, whose name is carefully redacted in declassified files, refers to Shilling's washer as a plumber's bodge that may temporarily mask symptoms while creating catastrophic failure modes we haven't yet identified. The phrase Miss Shilling's Orifice emerges during this period, and it's not meant as a compliment. RF mechanics adopt it first, half mocking the idea that a problem requiring Rolls-Royce's best engineers can be solved by a woman with a drill press. The double entendre isn't subtle. It's 1940. Britain is fighting for survival, and institutional misogyny still finds time to express itself through innuendo. Shilling, to her credit, ignores the commentary entirely. She's too busy installing washers on every Spitfire that squadron leader Lane can authorise, and Lane is too busy keeping his pilots alive to care about what the engineering establishment thinks of field modifications. The first combat test happens on June 3rd, 1940, over Dunkirk. Flight Lieutenant James Coward, flying a modified Spitfire, engages a Bf-109E at 8,000 feet. The Messerschmitt pilot executes his standard escape manoeuvre, rolling inverted and pushing into a split S dive. Coward follows, stick forward, expecting his Merlin to cough and die. It hesitates for perhaps a second, runs rough, then catches and holds. He stays on the 100-known's tail through the entire dive, closes to 200 yards and fires a 3-second burst that tears through the German fighter's left wing route. The Messerschmitt spins into the channel. Coward returns to Duxford and files a report that reads, "Engine modification performs as advertised. Maintain pursuit through negative G manoeuvre that would previously have forced break-off. Recommend immediate installation across squadron." By mid-June, word spreads through fighter command like fire through dry timber. Pilots talk, and what they're saying is that 19 squadron Spitfires can suddenly do things that were impossible 3 weeks ago. Squadron commanders start calling Farnborough directly, bypassing official channels, demanding to know how they can get these washers for their aircraft. The RA establishment digs in, insisting on comprehensive testing protocols, failure mode analysis, and certification procedures that would take months. Air Chief Marshal Hugh Dowding, commanding Fighter Command, cuts through the bureaucracy with a directive dated June 22nd. Install Shilling's modification on all operational Spitfires immediately. Testing protocols can follow later. Right now, pilots need every advantage they can get. Production and installation become the bottleneck. Manufacturing brass washers to 0.060-inch precision isn't technically difficult, but Britain's machine shops are already running 3 shifts producing everything from bomb fuses to gun barrels. Shilling personally supervises production of the first batch, 5,000 washers manufactured by a Birmingham metalworks that normally makes plumbing fixtures. The irony of producing an aerospace modification in a plumbing factory isn't lost on anyone. Installation teams move from airfield to airfield, modifying aircraft between combat sorties. A Spitfire lands, gets rearmed and refueled, and while the pilot is in the dispersal hut drinking tea and filling out combat reports, a mechanic is under the cowling installing a threepence brass disc that might save that pilot's life on the next sortie. By August 1st, 1940, approximately 70% of operational Spitfires carry the modification. Combat reports from the intensifying air battles show measurable improvement. Pilots are pursuing more aggressively, staying engaged through maneuvers that would previously have forced disengagement. The negative G engine cut still happens, but it's become a momentary hesitation rather than a mission-ending failure. More importantly, RAF pilots are learning they can trust their aircraft to follow their instincts. That psychological shift matters as much as the mechanical fix. A pilot who knows his engine will quit if he pushes forward is a pilot who second-guesses every tactical decision. A pilot who knows his engine will hesitate but hold is a pilot who fights without internal doubt, eating away at his reaction time. The proof arrives in blood and wreckage scattered across the Channel. On August 11, 1940, the day the Luftwaffe designates as Adlertag, Eagle Day, the beginning of their concerted campaign to destroy the RAF, the tactical equation has shifted in ways German intelligence hasn't detected. Oberleutnant Franz von Werra, an experienced Bf 109 pilot with 13 confirmed kills, engages a Spitfire from 72 Squadron over Dover at 12,000 feet. He executes the maneuver that has worked flawlessly for 4 months, inverted roll into a negative G dive, forcing the British pilot to either break off or follow into an engine failure. Spitfire follows. Von Werra expects to see the telltale black smoke of a Merlin engine cutting out. Instead, the British fighter stays locked to his tail, closing the distance. Von Werra pulls into a climbing turn, but he's already defensive, reacting instead of dictating. The Spitfire pilot, Pilot Officer Ronald Hamlin, fires a 4-second burst at 150 yards. Cannon shells rip through Von Werra's cockpit canopy and engine cowling. He belly lands in a Kent pasture and becomes a prisoner of war. Von Werra will eventually escape British custody and make it back to Germany, where he files detailed reports about the engagement. Luftwaffe intelligence initially dismisses his claims that Spitfires can now follow through negative G maneuvers. The Merlin carburetor problem is documented fact, verified through interrogations of RAF prisoners and technical assessment of captured aircraft. What the Germans don't know is that those assessments are based on Spitfires captured in May and June, before Shilling's modification reached operational squadrons.